Thank you very much for giving me the opportunity to speak at this my first American seminar, I guess. Not live, but yeah, I'm here from Vienna. But yeah, so today I want to talk about my first project as a PhD student of Michael Pinskas. And I want to somehow talk about graph orientation problems. First, I want to introduce them to people who have not seen them before. They're very easy to introduce, and so that's nice. Then I want to explain how those graph orientation problems can be viewed as CSPs of certain structures, namely of first order reducts of finitely bounded homogeneous structures. And then I will very roughly sketch how one can obtain complexity dichotomies um, for those structures. So for essentially for the graph orientation problem. And along the way, I guess I'll introduce very key techniques used in the study of those first order reducts of finitely bounded homogeneous structures, and yeah, sort of what the main results are to tackle those problems. Okay. So let's start with the graph orientation problem. So this is you're given just a finite set of finite directed graphs. So every vertex has a unique orientation. And the F-free graph orientation problem, OP of F, is the following decision problem. You're given a finite graph G as input, and you're supposed to decide, does this graph G admit an orientation that does not embed any member of F? So can you orient the vertices such that none of the forbidden pattern occurs? Okay, so I guess this is easy enough. Let's look at examples. So very easy example. You forbid the cycle, the 3 cycle, and then also you forbid this cyclic 4 tournament. So tournament is a directed complete graph. So what are we supposed to answer in this case? Well, actually, in this case, we don't even need to the answer doesn't even depend on the input graph G. We can always answer yes. Why? Well, if we're given a finite graph G, we just orient the vertices of this graph along a linear order. So in my picture, I denote this from sort of, I imagine that the linear order goes from bottom to top. And then I orient the edges such that every edge is increasing. So always points to the vertex of which is larger. And I mean, naturally, this will induce an acyclic orientation of the graph. So G prime is the orientation. And well, both of the forbidden structures here, both of the forbidden patterns, they have a cycle, so they cannot possibly embed into G prime. So yeah, we can, oops, we can always answer yes. Every graph has an acyclic orientation, so it's solvable in constant time. So what about this set F, where I forbid again the 3 cycle, C3, and I also forbid the transitive 4 tournament, so linear order on 4 vertices. What should be the answer here? Well, in this case, the answer depends on the input graph, and namely, the input graph can always be oriented in an F-free way, if and only if the graph does not contain a fork-leak. Okay, why is that? So, I mean, this would give that the graph F-free orientation problem in this case is solvable in polynomial time, because you can always check in polynomial time if a graph contains a fork-leak. You just need to go through all the four element subsets of the graph and check if there are edges everywhere. And there are only polynomially many four element subsets of input graph. Well, the thing is the three cycle C3 or the transitive 4 tournament embed into every orientation of K4. So K4 cannot possibly orient it in a way that is F3 in this case. So if our input graph contains a 4-click, we cannot give an orientation which is F3. But if the input graph is actually K4, does not contain a 4-click, then we can again just choose an acyclic orientation of the edges and C3. T4 cannot embed because it does not have a 4-click, and C3 cannot embed because it's cyclic and the orientation is acyclic. Oh no, no, it's there again. That's gone. Okay. Okay, a last example. Now a bit more involved. We forbid this three walk and again the 3 cycle. And in this case, we are supposed to answer yes if and only if the input graph is 3-colorable. This actually follows from a theorem proved by many different mathematicians. So, I mean, it was independently proved by Galai, Hasselroy, and Vitaver. And famously, the 3-coloring problem is NP-complete. So we also get that. Actually, in this case, it's quite elementary to see. It's quite elementary to see why it's quite elementary to see why we can so why this F3 orientation problem is equivalent to the 3-coloring problem. So if we start with a graph G, then this graph is 3-colorable. I mean, sort of depending on the definition, but I mean, some people might define it in that way, if it homomorphically maps into the triangle graph. And having a homomorphism from G into the triangle graph, this is equivalent to an orientation G prime, such that we have a homomorphism of oriented graphs from G prime into this acyclic orientation of the triangle. If we start with this graph homomorphism H from G to the triangle, then we choose an arbitrary acyclic orientation of the triangle and pull this orientation back along the graph homomorphism. So if we have an edge in the graph G, and this is mapped to an increasing edge in the acyclic orientation of the triangle, we orient it in an increasing way. And if it's oriented in a decreasing way, so if it's mapped to an edge that's decreasing, we orient it in a decreasing way. And if we have a homomorphism, on the other hand, of those oriented graphs, we just symmetrize all the edges to get again a graph homomorphism from G into the triangle. So this is basically the same. And also an orientation G prime mapping into the acyclic triangle. This is basically the same as an F3 orientation G prime. So why is that? Well, if we have an orientation G prime that homomorphically maps into this acyclic triangle, then neither the three walk or the cyclic orientation of the triangle can possibly homomorphically map into G prime. Because if they were to map into G prime, or if they were to embed into G prime, then they would homomorphically map into the acyclic orientation of the triangle. And both do not actually homomorphically map into the acyclic orientation of the triangle. If, on the other hand, we're given an F3 orientation G prime of G, then we can define a mapping into the acyclic orientation of the triangle by mapping all the sources of G prime. So all the vertices where you only have outgoing edges, you map it to the lower left vertex. You map all the sinks of G prime to the upper vertex. And everything that's left, you map to the lower right vertex. And it's then easy to check that this is actually a well-defined homomorphism of oriented graphs. Okay. So now we've seen that the graph orientation can be NP-complete or it can be polynomial time solvable, being constant time solvable, obviously being a special case of polynomial time solvability. And this was actually proved by Manuel Budierski and Santiago Guzman Pro in 2023. If the set F of forbidden structures consists of tournaments only. So they proved that if F consists of tournaments only, then the graph orientation problem OP of F is either tractable or NP complete. So this either obviously under the assumption that P is not equal to NP. All right. So this is the graph orientation problem. Are there any questions about that so far? Okay, I guess not. And then let's continue. Now we look at the graph orientation completion problem. So the graph orientation completion problem, now as input, we are not given a finite graph G, but a finite graph G with a partial orientation of the edges. So I mean by that some of the edges already have an orientation and some of the edges do not. So this is what I mean with a partial orientation. And then we're asked to decide, can this partial orientation of the edges be extended to an F-free orientation of the whole graph G that is F-free? Okay. And again, basically in the same paper, I think it's a different theorem in the paper, but again, by this work by Manuel Budierski and Santiago Guzman Pro, we know that if F consists of finite tournaments only, then the orientation completion problem is either tractable, so solvable in polynomial time, or it's NP complete. Okay. In the beginning, I briefly mentioned that I want to talk about how the graph orientation and the graph orientation completion problem can be modeled as constraint satisfactions, or CSP for short, of relational structures. And I mean, naturally, I need to introduce CSP at one point of the talk. I know Sebastian last week, he also defined constraint satisfaction problems, but he defined them in a slightly different way than I'm gonna introduce them. So I mean, even if you've seen his talk, then maybe this is gonna be a new perspective, or you already know constraint satisfaction problems quite well. So then this will just be a recap. I wasn't sure if everyone here was super familiar with those. So what is a CSP, a constraint satisfaction problem? Well, we're given a relational structure in some relational signature tau. And one way of viewing the CSP is just the CSP of A is just the class of finite tau structures which homomorphically map into A. But I also mean, or I'm also going to talk about the CSP as a decision problem. And then I'm supposed to decide, given a finite tau structure B, does this lie in the class CSP of A? So does B homomorphically map into A? And yeah, this is the constraint satisfaction problem of A. A is oftentimes called the template of the CSP. So again, let's look at some examples. I already mentioned, I think, this earlier. If we take as a template K3, so the triangle graph, then the CSP of K3, this will be the three coloring problem. So a finite graph maps into K3, and if and only if it has a three coloring. And I mean, technically, as inputs for the decision problem CSP of K3, we not only get graphs, but I mean, some of the edges might have a unique orientation, and some of the edges might be symmetric. But I mean, then if we just answer yes if and only if the symmetrized version of our input is three colorable, and no otherwise, right? So another classic example, the the CSP of the rationals with order. And well, this is essentially amounts to deciding if the input is an oriented acyclic graph. And the last little example, I mean, CSPs can also model quite difficult questions, in fact, undecidable questions. So the CSP of the integers with unary predicates for 0 and 1, and then ternary relations plus and times. With this template, we can essentially, we can not essentially, but we can encode Diophantine equations, or when Diophantine equations have integer solutions. And I mean, this is famously undecidable. So I mean, CSPs, they cover a whole array of decision problems. Okay. So how do CSPs relate to the graph orientation problem or the orientation completion problem? This was also done. This observation is due to Manuel Budierski and Santiago Guzman-Fro in their paper from 2023. Namely, they observed that if F, the set of forbidden patterns, in this case tournaments only, so if F consists of tournaments only, then the graph orientation problem of F and the orientation completion problem of F, those are CSPs of suitable infinite structures. And well, those templates, so those infinite structures, are quite easy to construct actually, and they're constructed using Fresay's theorem. And yeah, this is, I think it's nice to somehow see how the construction works, because it's, I mean, it's quite elementary, and also I think, me personally, I think Fresay's theorem is a very nice result. So I'm going to briefly introduce it, not in its full generality, but rather introduce a version which is used for our purposes. So what does Fresay's theorem say? Well, first we need to define what a so-called Fresay class is. So you're given curly C, a class of finite tau structures. Again, tau is a relational language. There's also a version of Fresay's theorem with also relations and functions in the signature, but this one is this formulation is even easier, and I just need the relational version, so I'm gonna stick to relational language here. So anyways, so this class curly C is called a Fresay class if it satisfies the following three properties. The first property being that C is hereditary, which means that if you're given a finite structure A in curly C, and you have an embedding from B into A, so embeddings being homomorphisms which both preserve and reflect all the relations, where you have such an embedding, then we also want that B, the finite structure B, lies up to isomorphism in the class curly C. So you could view this as sort of the class C is closed under substructures. This is really what it is. And next, we're gonna ask C to be essentially countable, which just means up to isomorphism, there are only countably many structures in C. And the third most important property C has to satisfy is the so-called amalgamation property. So suppose you're given structures A, B1, B2, and embeddings from A to B1 and from A to B2. I depicted them in this right-angled diagram. So you have this of structures in curly C. Then we always require that there is a structure C and embeddings. So this structure C has to lie in curly C, such that we have embeddings from B1 into C and from B2 into C, such that the depicted diagram here on the right, that this is commutative. And since, I mean, if we have a Fresay class and we ask it to be hereditary, then this structure C can actually be taken to to be the image of B1 and B2 of those two embeddings to be the joint image. So this amalgamation property really says if you have structures B1 and B2 in curly C with a common substructure A, I mean, this is realized by the embedding from A into B1 and B2, that along A you can glue them together and still remain in the structure curly C, in the class curly C. So again, let's look at some easy examples of Fresay classes. The class of all finite sets trivially is a Fresay class. The class of all finite graphs is a Fresay class. I mean, this amalgamation, you have two graphs which overlap somehow. You just glue them together disjointly, except for on their overlap. Then also the class of finite Kn free graphs, so Kn being the complete graph on n vertices. This is also a Fresay class. Also a very famous example, finite linear orders, and also all fields of some characteristic P. Those will all be Fresay classes. Here that the finite fields of characteristic P, I believe you need to phrase it with a functional language. So you need to have plus and times, and you don't want to encode this as relations, but you really want to encode this as functions. But earlier I said that Fresay's theorem also holds for functional languages. You just need an additional property. But finite fields of characteristic P also satisfy this property. And now what does Fresay's theorem say? Well, Fresay's theorem says that if you have a Fresay class C consisting of tau structures, then there is a countable homogeneous tau structure, which we call the Fresay limit, so flim of curly C, which is unique up to isomorphism. And well, the property which the Fresay limit has to satisfy is that the finite substructures of this Fresay limit are precisely up to isomorphism again the elements of curly C. And yeah, I didn't want to put the definition of homogeneous here on the slide, but this just means if you have in C, sorry, in the Fresay limit of C, if you have more generally, a structure is called homogeneous if whenever you have two subset of this structure which are isomorphic, then an isomorphism of those finite substructures can be extended to an automorphism of the whole structure. So that's what it means to be homogeneous. Again, let's look at the previous examples and determine the Fresay limits. Well, the Fresay limit of all finite sets, this is just omega, or just a countable set. The Fresay limit of all finite graphs famously is the Rado, or the random graph. I mean, random graph it's also called because somehow you just look at a countable set, and for every pair of points in the set, you flip a coin, probability 1/2, to determine if there's supposed to be an edge on a non-edge, and almost surely you're going to end up with the random graph. The Fresay limit of the class of finite Kn-free graphs, this will be the so-called Hansen graphs. The Fresay limit of finite linear orders, this will be just the rationals with order, or any countable dense linear order with any countable dense linear orders, which by the theorem is then isomorphic to Q with order. And the Fresay limit of all finite fields of characteristic P, this will just be the algebraic closure of Fp. All right, so this is Fresay's theorem. And how do we use this to build a template of of the F-free graph orientation problem? Well, again, if we're given F a finite set of tournaments, then the class curly C of F will be a Fresset class. Well, I didn't say, I guess what, so curly C of F is the class of finite F-free directed graphs, and this will be a Fresset class. Well, why is that? Well, obviously, if you have a F-free directed graph and you look at a subgraph, this will again be F-free. Also, this is essentially countable because, I mean, there are just finitely many up to isomorphism directed graphs on n vertices. So, I mean, essential countability is for free here. And also they have the amalgamation property. Well, so, I mean, I want to briefly sketch why that is the case. Suppose you have B1 and B2 finite F-free directed graphs. And they overlap in A, which again is a finite F-free graph by the hereditary property. How do we glue them together to still have an F-free oriented F-free directed graph? Well, we just glue them together in a way that there are just no edges between the points in B1 and the points in B2 which don't lie in A. So yeah, in this, I don't know if you see my mouse cursor here. Probably not. Is there a laser?
Yes, we do.
Yeah, you do. Excellent. Okay. So I mean that there are just no edges between here and here. I mean, there are obviously edges from here to here and from here to here, but from here to here, there are just no edges. And why is that again F-free? Well, suppose you have an embedding of some tournament into this big directed graph. In a tournament, every pair of vertices has an edge between them. So we cannot possibly be in the situation that a tournament maps one vertex into here and another into here. So a tournament always has to be within B1 or within B2. So if we had an embedding from a tournament into this whole thing here, this would be an embedding of the tournament into one of the two graphs, which by assumption are F-free. Okay, so the class curly C of F, curly CF is actually a Fresset class. So we can build the Fresset limit, which I denote here by df. So this will, yeah, I wrote it down here. So we'll have a set V of vertices and then have a set of edges which are oriented. That's why I denoted it with an arrow. And this is sort of the universal homogeneous F-free directed graph, the countable homogeneous universal F-free graph. And its graph reduct we denote by HF. So this will again have the same set of vertices, and then we symmetrize the edge relations. So we take edge pointing, I mean, we take all the edges into the right, and then we just, yeah, I mean, we symmetrize them. And this is, in particular, this is a first order reduct of the graph DF. So this can, I mean, this union arrow pointing in the one way and arrow pointing in the other way, where by arrow pointing in the other way, I obviously mean the flipped relation. This can be expressed by a first order formula, and in fact a quantifier free formula. So this will be a first order reduct. And now, I mean, we can observe that the CSP of HF, which by definition is just the finite graphs which homomorphically map into HF, that this is precisely the set of graphs that admit an F-free orientation. And I mean, I don't know actually why I put here this third set here. Actually, it's, I mean, you can immediately see that the set of finite graphs which homomorphically map into HF, that this is exactly the set of finite graphs that admit an F-free orientation, namely if you have such a homomorphism from G into HF. Again, as in the early example I gave, HF has an F-free orientation, namely DF. And this orientation, you pull back along this graph homomorphism to G, and then it's easy to see that this orientation one obtains is actually F-free. And conversely, if we have an F-free orientation of our graph, then we know that it actually embeds into DF, and such an embedding then will induce embeddings of the underlying graphs. So actually the CSP of HF is precisely the graph orientation problem of F. And in a similar spirit, or basically by the same argument, the graph orientation completion problem of F, this is the CSP of HF together together with the edge relation, the oriented edge relation still in place. So if we, for example, if we're given as input for the orientation completion problem, we're given a graph and a partial embedding which just doesn't enforce any orientations of the vertices whatsoever, then we just take we encode this as the graph together with an empty set of oriented edges. If we already have all the edges oriented in a certain way, so this is not a partial orientation but an orientation already, we have that the edge relation has to cover actually all the edges in the graph. Okay. Are there any questions about this so far? Okay, good. Then another a last thing I want to mention about this class CF, or the graph HF we just built. Namely, this class CF of finite directed F-free graphs, this is what's called finitely bounded. And by this I mean that there is some large integer k, or some integer k, which has the following property, namely, we can check if a finite directed graph, if a finite tau structure B lies in CF, so if it's a finite directed F-free graph, if and only if all substructures of B of size less or equal than K belong to the class CF. So if all substructures of size smaller or equal than K are finite directed F-free graphs. Why is that? Well, in this case, we just need to take K to be the maximum of 2 and the size of the largest tournament in F. I mean, if we're given this input B, then we know K is at least 2, so we can check if all the edges are actually directed edges, so if they have a unique orientation. That's why we need the 2 here. And then, since we know that K is larger than the size of, or larger or equal than the size of the largest tournament in F, we can just look at all the substructures of size K of B and check if there occurs a forbidden tournament. And if this does not happen, then by definition, B is F-free. So yeah, the class CF is finitely bounded. Why do I mention that? Well, there's this so-called tractability conjecture, which is formulated, which was first formulated by Emanuel Budierski and Michael Pinsker in 2011, which claims that If A is a first order reduct of a finitely bounded homogeneous structure, here finitely bounded, a homogeneous structure is finitely bounded if and only if the class of finite substructures is finitely bounded. So if A is such a first order reduct, then the constraint satisfaction problem of A is either tractable, so solvable in polynomial time, or NP complete. We just checked that the class CF is finitely bounded, so the directed graph DF classifies as finitely bounded. So and HF and also the HF together with the oriented edge, those are both first order reducts of DF. So they're actually in the scope of this conjecture. So yeah, it's actually, you could say it's no surprise that you have such a complexity dichotomy. What's, however, the case is that the proof by Emanuel Budieski and Santiago Guzman Pro, this does not use a recently developed technique or theory, which was developed sort of to tackle this tractability conjecture, but was sort of rather proved by an ad hoc reduction. And well, now I want to briefly explain why why we actually reproved the theorem by Bodesky and Guzman Pro, a part of the fact that I was just starting my PhD and sort of was a nice nice beginning project. Well, as I mentioned, for the scope of this tractability conjecture, there was this theory developed which is called smooth approximations, and we wanted to see if this smooth approximations can actually handle this case of the graph orientation problem, because if it wouldn't handle sort of such an easy example, then I mean, yeah, it would need some serious reconstruction somehow. And well, the advantage of reproving the theorem using the smooth approximations, the advantage of this would be that it would then hopefully align with previous applications of the theory, so that one could maybe see a way how one can tackle in the future this tractability conjecture, somehow see different patterns but also see what different problems arise. Another benefit of using the smooth approximations for this graph orientation problem is that this sort of provides a very structured view on the matter. So if in the future you would want to generalize this graph orientation problem, then hopefully such generalizations won't be as difficult as previously if you only have this ad hoc reduction. Namely, natural generalizations would include that f we don't. I mean, in this result here, we ask f to consist of tournaments only, but it's, I guess, very natural to relax this and just ask f to consist of directed graphs. So hopefully this will be possible. Yeah, this problem will also be possible to tackle. And also, edge coloring problems are very prominent in this infinite domain CSP questions. So you're given a graph and you want to color the edges of the graph so that not of a certain previously fixed patterns occur. And I mean, orient edges of a graph and coloring edges of a graph is a very similar problem. So hopefully, if we have a very structured proof, then it can easily be generalized to such edge coloring problems. Okay. And well, this also then provides the previous examples that were proved using the smooth approximations were reducts of very easy structures. And this would sort of be one of the the harder structures which have been this theory of smooth approximations has been applied to this day. Okay. Are there any questions so far? So I'm supposed to finish at 10:15, correct? So 50 minutes.
That's right.
Okay. Well, in the classifications of the complexity of constraint satisfactions in general, so-called polymorphisms have played a very important role. And I will now briefly try to sketch why polymorphisms are so important and why they can be viewed as sort of symmetries of a constraint satisfaction problem. Well, I claim that the computational complexity of the CSP of A is captured by the polymorphism clone pol A. And the polymorphism clone pol A consists of all homomorphisms of finite powers of A into A itself. So the set here. And why is that? Well, if you have a tau structure, so tau being the signature of A, if you have a tau structure B and homomorphisms H1 to Hn from B into A, which you can view as solutions to the CSP, and you take any polymorphism of A of arity n, then you can apply this polymorphism F to those homomorphisms H1 to Hn and obtain potentially a new homomorphism B of B into A. So the polymorphism act on the solution space of a CSP to a previously fixed instance. And whenever you have symmetry around, you can expect that computational problems will become easier. I mean, if you think of linear equations, systems of linear equations, then solution spaces of those are highly symmetric. They're just affine spaces. And I mean, we all know that linear systems of linear equations over fields are solvable in polynomial time. On the other hand, if you only have few symmetries, then to get solutions to a CSP, a lot of unstructured search is necessary. So in general, you would expect that the CSP becomes harder. So yeah, this is sort of the hand wavy explanation, and this can actually be made precise by this theorem from 2017. If you have an omega categorical tau structure A, omega categorical here sort of is an approximation of finiteness. So A is it's an infinite structure, but behaves reasonably finite in a way that only has trivial symmetries, in the sense that the polymorphism clone of A admits a uniformly continuous uniformly continuous minion homomorphism into the clone of projections. Here, projections means just the clone of all projections on a two-element set. Then the CSP of A is NP complete. And here, I think I don't want to really go into this details, but here, I mean, the polymorphism clone of A is and also the polymorphism clone of projections, they come naturally equipped with uniform structures, and then well, you can ask for this clone homomorphism, or this minion homomorphism, to be uniformly continuous. I spelled this out here, but this is actually not really needed in the following. And the minion homomorphism, I think also Sebastian defined this last week, but it sort of says that not all compositions are respected by this homomorphism phi, but if you have F on the left and you just plug in projections, so those pi I to the k, this will be k-ary projections, then this map phi actually preserves those. So this is what is a minion homomorphism, but you should really view this as the CSPA only has trivial symmetries. And conversely, in the resolution of the finite domain CSP dichotomy conjecture, it was proved that if you have a finite template of a CSPA, then this CSP is tractable if and only if you have a polymorphism which is cyclic. So you have some map F which satisfies, so you can cyclically shift the arguments and obtain the same thing. And this is then what we proved is a generalization of this graph orientation problem, if you will. So you're given a finite set of tournaments and relations R1 and up to Rn, which are first order definable in the directed graph df, which consists of tuples inducing tournaments in the graph HF. And then exactly one of the two statements hold. On the one hand, A has only, so HF together with those relations has only trivial symmetries. So there's this uniformly continuous minion homomorphism into the projections. And in this case, CSP of A is NP complete. And on the other hand, if the polymorphism clone contains what's called a canonical ternary function, I think I don't have the time to go into details what this means. But this canonical function sort of helps reduce the infinite CSP to a finite CSP, and the canonical functions will then induce polymorphisms of this finite CSP one reduces to. So if you have a canonical ternary function in the polymorphism clone, which is cyclic, then the CSP of HF together with the relations R1 to Rn, that this is in P. So it's tractable. So what does this theorem give us? If we don't choose any of the relations Ri whatsoever, then we just have the CSP of HF, which is the F-free orientation problem. If we take R to be just the edge relation, as I said earlier, then this will give you the orientation completion problem. But we could also, for example, let R be this set. So we look at triples X, Y, Z, such that you either have them, there's an edge from X to Y, from Y to Z, and from Z to X, or there's an edge from Z to X, from X to Z, from Z to Y, from Y to Z. And this will be an orientation problem where some marked 3 clicks have to be oriented in a cyclic way. So as a last thing, let's quickly look at what I exactly mean by that. Expand a bit on this example. So again, R is this relation I already talked about. And what do instances to the CSP of HF together with R look like? This will be a set of vertices, a set of edges, and then a set of ternary relations R1. Here I chose 4, R1, R2, R3, and R4. And here the vertices are denoted by points. Then you have the edges. And then I want that those three vertices are mapped to R, that those 3 vertices here are mapped to R, that those 3 vertices, and that those 3 vertices are mapped to R. So they need to have cyclic orientations. So what is the solution to this instance? Well, this is just an orientation such that we have here there will only be cyclic orientations. And this is achieved by these orientations. Okay, I guess I stop here. I somehow miscalculated the time a bit. Maybe also spoke a bit too slow, but yeah, thank you anyways for your attention. And if you have any questions, please feel free to ask them.